Okay, now we're going to look at what we're going to call generalized Hooke's law. We're going to kind of bring together everything that we've talked about for the past couple of lectures. Okay, so we know from dealing with Poisson's ratio that we can say that Poisson's ratio is the negative of the lateral strain over the longitudinal strain. And if we're going to say that we're just, in this example, pulling along the x direction, that would be the negative strain in the y divided by x, or negative strain in the z divided by x, since they're both the same. They're both going to be the same in the off-axis. And so we also know that Hooke's law for normal stress tells us that stress in the x direction would be the modulus of elasticity, or Young's modulus times the strain in the x direction, which we again can rewrite and say, okay, well, that's the strain in the x direction divided by the stress in the x direction divided by the modulus of elasticity. So, by taking this, we can go and we can plug it back into here, and let's just Poisson's ratio is negative strain in y divided by strain in x divided by modulus of elasticity. And then I can rewrite this to go, okay, well, the strain in the y, which is also the strain in the z, is going to be equal to negative Poisson's ratio, the stress in the x direction, divided by the modulus of elasticity. So what we can do is we can set up strain as just a function of the normal stress. Now, something to stress, not meaning to be a pun there, but something to stress with this only works when it's in the linear elastic region. Why do I say that? It's because of this equation here. Because everything that we're doing right now is based off of Hooke's law for normal stress, which only applies in the linear elastic region. Once you start plastically deforming the material, this relationship doesn't hold any longer. So let's look at what happens when I start applying a force to multiple axes. What if I have a stress in the x, a stress in the y, and a stress in the z? This is where I can use my law, my method of my principle of superposition. And that's where we can figure out each individual one and calculate out what its effect's going to be, and then add everything together. So this requires a couple things. One, the strain is linear related to the stress, i.e., we're in the linear elastic region, and therefore Hooke's law applies. And the other ones, the deformations are relatively small. And this kind of goes along with the first one, because if we have large deformations, we're really not in the linear elastic region any longer. We'll now be plastically deforming it, probably well on our way to breaking the material. Okay, so let's look at everything. And so I'm going to break this up a little bit, make a little table. So we'll have our strains here. And then we're going to look at the force. So force applied in the x direction, force applied in the y direction, force applied in the z direction. So we're going to start out with our strain in x. If we apply a force in the x direction, what's the strain going to be? Well, it's going to be the normal stress divided by the modulus of elasticity. So now if I'm looking at a force that's applied in the y direction, how's that going to change the x strain? Well, as we just talked about, we can sit there and go, okay, well, the negative of the Poisson's ratio times that stress in the y direction divided by the modulus of elasticity. So this is how much strain that we'll have in the x direction because we're pulling a force in the y direction. So that's that off-axis shrinkage, which is why it's negative. Same thing happens in the z direction. Negative stress in the z divided by modulus elasticity. We can do the same thing for strain in the y. we can just start here and go, well, the normal strain, just from the force, is going to be the stress of y divided by the modulus, and then we come over here and go, okay, well, negative Poisson's ratio, stress in the x direction, divided by E, negative Poisson's ratio, stress in the z direction, divided by E. And the same thing, we'll go to EZ, the normal strain is going to be the normal stress divided by the modulus, so I'll subtract from that Poisson's stress in the x divided by E, minus Poisson's stress in the y direction divided by E. And so what do? We just add them up. Superposition. Oops. I'm losing my... add that there, and there we go. This will give us the complete state of strain at any one point within our thing. What happens if we don't apply a force? If there's no z force, well, we just knock all this out. And then you just have x and y. What if you have no y force? Well, you just knock that out. What if you have no y and z? Well, you knock that out. And there's what your strands are going to be. So this is our generalized Hooke's law. And I actually have... there we go. I've got it listed out just in case you want to see it without my writing, so it's a little bit clearer. So no matter what force that we put on this thing, we can calculate out what the deformations are going to be, especially the off-axis deformations.